ME350 Example Problem for Extended Surfaces, or FIN, analysis. A rectangular plate with an equal width and height of 12 millimeters cannot exceed a temperature of 75 degrees Celsius. So aluminum pin fins with known thermal conductivity and dimensions are to be attached to the surface. The plate and fins are exposed to ambient air at 30 degrees Celsius with a convection coefficient of 40 watts per meter squared Kelvin. The total heat transfer rate from the surface is 1 watt. For part A, calculate the efficiency and effectiveness of each fin. For part B, calculate the number of fins that must be attached to the plate. For part C, calculate the overall efficiency for the fin array. Finally, for part D, calculate the temperature at the base and tip of each fin. Our first assumption for this problem is steady state, which means that none of the properties are changing with time. Our second assumption is one-dimensional conduction in the x direction only, which is reasonable for a thin fin where the resistance to conduction along the fin is low compared to the resistance to convection from the sides. Our third assumption is constant properties, which is reasonable as long as the properties have less than a 10% variation over the range of conditions. Our fourth assumption is that there is no internal heat generation, which is to be expected for fins that are used to enhance heat transfer and reduce operating temperatures. Our fifth assumption for this problem is negligible radiation for the exterior boundary. This is a reasonable assumption for an opaque wall and for moderate temperatures combined with significant convection at the exterior boundary. Our sixth assumption is negligible contact resistance between the base and fins. This is typically true for fin arrays that are made out of one continuous material. For part A, we will first find the fin efficiency, which is defined as the heat transfer for our actual fin compared to the maximum possible. We begin by using table 3.5 to get the equation for the fin efficiency for fins with constant cross-sectional area and with an active tip in terms of the parameter m and the corrected fin length. Note that P is the perimeter, A sub c is the cross-sectional area, L sub c is the corrected fin length, and A sub f is the fin surface area for convection, which are defined for our pin fin on the drawing on the right. Substituting in, we get a value of 23.95 per meter for M and a value of 15.375 millimeters for L sub c. Recall that the corrected fin length accounts for convection from the tip by adding additional length to the fin to account for the additional area for convection. Using these values for M and L sub c, we calculate a fin efficiency of 95.7%, which is a typical value for a good fin. Continuing with part A, we want to find the fin effectiveness, which is defined as the heat transfer for our actual fin compared to the heat transfer from the base without a fin, as shown. Substituting in for the heat transfer from the actual fin in terms of the fin efficiency and our pin-fin geometry, this equation reduces to the one shown. Substituting in, we get a value of 39.2 for the fin effectiveness. This means that there is 39.2 times more heat transfer with the fin than without, and that this is a very effective fin. For part B, we want to find the number of fins that we need to attach to the base to ensure that it does not exceed the maximum operating temperature. For this analysis, it is convenient to use a resistance analogy. We begin by drawing a resistance network. The first node on the left is labeled T sub B for the base temperature. Then we have two resistors in parallel, one for the end fins in the array and one for the exposed base. And then we have the node on the right labeled T sub infinity for the temperature of the surrounding fluid. Finally, an arrow is added to indicate the total heat transfer through the fin array and then out to the fluid. Note that this resistance network would look the same either with or without an active tip. This is because the convection from the sides of the fins is to a fluid at T sub infinity, which is the same as for the active tip. For our calculations, We begin by calculating the maximum temperature difference for the array, which is 45 degrees Celsius. Second, we calculate that to remove the specified 1 watt of power, the overall thermal resistance of the array must be below 45 degrees Celsius per watt. Third, we write an equation for the overall thermal resistance in terms of the two thermal resistances in parallel. Fourth, we substitute in the definitions for the thermal resistances for N fins in parallel and convection from the exposed base. Solving for N, we get the resulting equation. Next, we calculate the fin area and cross-sectional area for the pin fin. Substituting in these values, we get that we need a minimum of 6.09 fins. For part C, we want to find the overall efficiency for the fin array, which is defined as the total heat transfer for the actual fin array compared to the maximum possible. From our resistance network and an analogy to Ohm's law, we substitute in for the actual total heat transfer to get the simplified result shown. For our calculations, I rounded the number of fins up to 7. Based on this, we calculate the exposed base area and total array area as shown. Substituting in values, we calculate the thermal resistance for our 7 fins to be 51.5 degrees Celsius per watt, the thermal resistance for the exposed base to be 190 degrees Celsius per watt, and finally our overall thermal resistance for the array to be 40.5 degrees Celsius per watt. Note that this is less than the maximum of 45 degrees Celsius per watt required to keep the temperature below the maximum because we rounded the number of fins up to 7. Finally, we substitute in to get an overall efficiency for the array of 96.6%, which is a typical value for a good fin array. For part D, we want to find the temperature at the base and tip of each fin. The base temperature can be found by again using the resistance network and an analogy to Ohm's law. From this calculation, we get that the base will be at 70.5 degrees Celsius. Again, this value is less than the maximum temperature of 75 degrees Celsius because we rounded the number of fins up to 7. To find the temperature at the tip of the fin, we will need to use the results presented in Table 3.4 from a fin analysis that assumes one-dimensional conduction and convection only, or we could repeat the derivation that was shown in lecture. From this table, we select the temperature distribution for case A for convection at the tip and substitute in x equal to L. Substituting in values, we get a tip temperature of 69.7 degrees Celsius. This is only slightly lower than the calculated base temperature of 70.5 degrees Celsius, which is expected for a high efficiency fin. For a first what-if analysis, we plot the number of fins required to remove 1 watt of heat from our surface versus the convection heat transfer coefficient. The dashed lines indicate the case we considered for this problem, where we used a convection coefficient of 40 watts per meter squared Kelvin, which corresponds to forced convection with gases, to get that we need 6.09 fins. If we rely just on natural convection, which has a convection coefficient of about 10 watts per meter squared Kelvin, we would need approximately 40 fins. Furthermore, once the convection coefficient is a little bit above 100 watts per meter squared Kelvin, which corresponds to convection with liquids, we would not need any fins. For a second what-if analysis, we plot the number of fins required to remove 1 watt of heat from our surface versus the fin length. The dashed lines indicate the case we considered for this problem, where we used a fin length of 15 millimeters to get that we needed 6.09 fins. Initially, for really short fins, we need over 50 fins. The number then decreases rapidly at first and then asymptotes towards needing no fins as L goes to infinity. Note that using fins with a length of around 10 millimeters would work well for this case because the number needed has already decreased significantly, but you have not reached the point where adding more length has minimal impact on the total number needed.